We are up to the solenoid. Now in your notes it says das Solenoid, so I want you to know that is just my ears hearing more of a German sound to solenoid and going with the German das, so it is just a solenoid or the solenoid. So make sure that you get that in there. I don't want you going to college and asking your professors where das Solenoid is. It is just a solenoid or the solenoid. We will come to understand the solenoid as the electromagnet, so we'll talk about that more in this course as well. But for right now, we need to understand a solenoid as a helical coil of wire. So if you just wrap wire around a cylinder, you have made a solenoid. And to help you out drawing these wires, I think of them as kind of backwards integral symbols. So if you just go to the top, you go to the top and make like a little backwards integral symbol, and then go to the top and make a backwards integral symbol. You can draw in your coils that way, so hopefully that helps. Now, when we do IDL cross R hat, so if we look at our IDL and we do a cross R hat into the center of the coil, so think of the going in the R hat going into the center of the coil. So our IDL cross R hat over here will give us a B field running to our right inside the coil. And why don't we mention outside the coil? Well, it turns out when you have many coils, you get the effect shown here, that the B field between the coils, so if you want, you can kind of circle this, you get B tends to cancel between the wires. And if you have many wires and they're very close, then you get the situation down here where we have what is called the ideal solenoid, which we will be working only with in this course. So we will not be working with a non-ideal solenoid. And you can see now how we kind of get the electromagnet out of the solenoid. So the B fields come out of north and go into south, and they will mirror the permanent magnet. So our ideal solenoid case simply means we have many wires very close together, so we will be assuming that the B field equals 0 outside the core. While this is an approximation, it is a really good approximation if you have long wires and you're near the center of the coil. And we will see on our next page of notes in a second here that B actually is constant inside the core. So let's go to our next page of notes to see why the B field is constant inside the core. Well, here we make our one exception to circular Amperian loops. We are going to use an Amperian rectangle because we want our Amperian loop at some point to mirror the B field. So what are we looking at here? Well, you're looking at a cross-section of the solenoid. So what you have to imagine is that kind of you took a saw and cut the solenoid in half the long way. So you're looking at a cross-section of the coil. The current is kind of going up the back here, out the front, and then into the bottom. So again, I don't really have it shaded here, but you're looking at kind of just cutting it in half that way. Well, you can be asked on the AP test to derive the B field inside the core of a solenoid, and you just have to know that this is our exception. We are going to use an Amperian loop where we are going to line up the loop such that, of course, it goes counterclockwise, but we are going to run one portion of the loop along the B field. That's important. And then we go perpendicular up. We go outside the solenoid. Outside the solenoid here. And then we complete our rectangle on the far side. So counterclockwise loop, and you definitely want to have one side of the rectangle parallel to the B field inside the core. So we get our B field here, and now we are going to perform our integral for Ampere's law, right? So when we're using Ampere's law to do a derivation, we use Ampere's law. Closed integral, line integral, b dot ds equals mu naught I enclosed. And we'll get to the I enclosed in a moment. So the I enclosed will be the number of coils times the current in each coil. We'll get to that in a second. But what we get with our Amperian loop rectangle is a really nice result, because we lose sections 4 and section 2 because the B field here and the DS's, right, are at 90 degrees to each other, and cosine of 90 is 0. And we lose section 3 because we are assuming we have an ideal solenoid and the B field is 0 outside. So we are just left with the core, where B comes out, because by symmetry there's no reason to expect to get a different B field value here, 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 right? And so it comes out constant by symmetry. So if you want to add by symmetry here, by symmetry, it comes out. We get the integral of ds is s. Now notice s is just whatever length h we took our Amperian loop to be, so it's an arbitrary variable at this point. So let's just leave it as an h. We just said that I enclosed is the number of coils times the current in each coil. And what we have here is, when we bring the h down, leave it as a variable, that is going to be, h is a length in meters, so we have the number of turns in that length h, which is going to give us the number of turns per length of the coil, and that is called the number density of turns, and we use that script n for that number density, so that when we replace this with that script n, the B field for the solenoid is mu naught script n I, where script n is the number of turns per unit length, and notice it is constant, it is not a function of r. So the B field for the solenoid, the graph will be a constant uniform B field inside the solenoid. It doesn't matter whether you're right at the center of the solenoid or near the edges. If you're inside the core, the B field is mu naught Ni, and the number density is the number of turns per length that usually is given as a parameter in the question, or you're given the information to calculate it. So there is our discussion of the solenoid, our derivation of the B field for the solenoid, and we will have some solenoid practice and move on.